Okay, picture this terrifying scenario. Imagine a massive short circuit on the power grid. The protection relay works perfectly, it detects the fault and fires off a trip command, but then the primary breaker mechanically jams. Its contacts are literally fused together, and that massive, destructive fault current just keeps on flowing. You see, every protection scheme we design fundamentally assumes that the hardware is actually going to work when told to. But what happens when it doesn't?
Welcome back to the Explainer. Today we're exploring the absolute ultimate safety net in power system protection, breaker failure, or the 50BF function. We're going to look closely at what happens when the backup plan itself is the thing that has to do the tripping.
Here's our roadmap for today. First, the ultimate safety net. Second, anatomy of a backup trip. Third, the timing trade-off. Fourth, proactive mechanical health. And finally, supervising the trip circuit. Let's jump right in.
Starting with Section 1, the ultimate safety net. Enter CCBR RFF. So, CCBR BRF, or if you prefer the ANSI standard, 50BF, is the breaker failure protection function. Its whole job is to detect when a primary breaker fails to interrupt a fault after it's been commanded to open. When it spots this failure, it initiates a backup clearing process by tripping the upstream breakers. It's there because a stuck breaker would leave a catastrophic fault energized indefinitely. Without this function, a single mechanical failure could literally destroy an entire substation.
I really love this analogy. Think of breaker failure protection like a building's secondary fire escape route. You hope you never, ever have to use it, right? Most days you walk right past it without a second thought. But on the day the primary exit is blocked by fire, it suddenly becomes the single most important piece of infrastructure in the whole building. It's the only thing standing between a contained, manageable incident and a total disaster.
Looking at the logic block here, you can see it doesn't just sit off in its own little world. The internal breaker failure protection block is deeply baked right into the broader busbar protection scheme. It constantly communicates with the trip logic and zone selection arrays to seamlessly route those emergency trip commands exactly where they need to go if that primary breaker fails.
Moving to Section 2, anatomy of a backup trip. Checking the current.
So how exactly does the relay know a breaker has failed? Well, it all happens in a very precise chain reaction. At T0, the relay issues a standard trip command, but it doesn't just assume the job is done. Instead, the relay's current check logic actively monitors the phase and residual currents, and it starts a timer. If that timer expires and the relay still sees fault current flowing, it knows for sure the primary breaker failed, and it instantly fires a backup trip command to the upstream breakers. Let's put this logic to the test. A trip command goes out. Fast forward 150 milliseconds, which is well past the normal operating time of a breaker, and significant phase current is still flowing. What exactly does the CCBR-BRF function do right at that moment?
Exactly that. It officially declares a breaker failure condition and immediately issues a backup trip command to the upstream breakers. Now, the severe consequence of this action is that it widens your outage footprint. You're aggressively isolating the fault by taking out way more of the grid than you originally intended. But it's an absolutely necessary trade-off to stop the ongoing destruction.
And this is where the digital logic meets physical hardware through the 86 lockout relay. When the breaker failure logic triggers, it usually hits one of these zone selection lockout relays. The 86 relay physically executes this massive backup command, stripping the busbar of all connected sources to clear that persistent fault once and for all.
Which brings us to Section 3, the timing trade-off, setting the clock.
So how long do we actually wait before pulling that emergency lever? Finding the Goldilocks zone here is absolutely crucial. A normal breaker might take 30 to 80 milliseconds to operate, while a typical failure timer is set between 100 and 200 milliseconds. If you set it too close to that 80 millisecond mark, you risk massive nuisance trips just because a perfectly healthy breaker was a tiny bit slow. But set it too long, you exponentially increase the severe physical damage to your transformers and conductors during a genuine fault. Literally, every extra millisecond a fault persists scales up the physical damage. To put this into perspective, let's look at some real-world commissioning parameters from an ABB RET615 relay. Engineers have to explicitly configure these current thresholds to detect a failure. They even choose the failure mode, meaning whether the relay relies purely on measuring current, checking the breaker's auxiliary status contacts, or a combo of both. It really grounds all this theory into hard commissioning reality.
All right, Section 4, Proactive Mechanical Health, SSBR.
But hey, What if we didn't have to wait for a catastrophic failure at all? This is where SSCBR comes in, which stands for Circuit Breaker Condition Monitoring. Instead of just waiting to catch a failed breaker during a fault, SSCBR monitors key performance indicators, things like operation times, wear, and spring charge times, to actually predict mechanical degradation before it happens. Its ultimate goal is to make sure our reactive 50BF safety net is never, ever forced into action. And our final piece, Section 5, Supervising the Trip Circuit Breaker, TCSSCBR. So we've covered the mechanical side, but what about the electrical pathway? Introducing TCSSCBR, or Trip Circuit Supervision. This function continuously monitors the integrity of the trip coil and all its associated wiring. Because think about this terrifying blind spot. You could have a perfectly healthy, well-lubricated mechanical breaker and a brilliant digital relay, but if the single copper control wire connecting the two is broken, that breaker is completely useless when a fault occurs.
TCSSCBR works tirelessly behind the scenes to prevent exactly that. It runs a continuous tiny test signal right through the trip wiring. And it's incredibly smart. It uses different electrical paths depending on whether the breaker is currently open or closed, meaning it leaves absolutely zero operational blind spots. If a wire breaks or control voltage drops, it doesn't wait for a fault, it triggers an immediate alarm.
Think of it like the small green power-on light on your smoke detector at home. It doesn't wait for your house to catch on fire to prove that the detector has power. It continuously confirms its readiness. Having that continuous confirmation is just vastly superior to waiting for an actual emergency to test your equipment.
Let's do a quick thought experiment to really lock this in. Imagine a circuit breaker sits closed, happily carrying normal load current for 3 months. Unbeknownst to anyone, a tripwire degrades and snaps during month 1. Without continuous trip circuit supervision, when is this creeping electrical failure actually discovered?
The terrifying reality? Potentially not until the next scheduled maintenance test. Or, way worse, during an actual fault when the relay is screaming at the breaker to trip and nothing happens. But with continuous supervision, that broken wire would have triggered a SCADA alarm within seconds during month 1, letting a technician fix it long before a short circuit ever occurred.
Which leaves us with this final thought for today's explainer. In your own protection schemes, are your safety nets secretly creating invisible blind spots while they wait for an emergency? Or are they continuously proving to you, second by second, that they are ready to catch you? Understanding how these internal logic blocks communicate is absolutely vital, and it primes us perfectly for our next exploration into the fascinating world of digital substation communications. Until next time, keep learning.